Okay, so welcome to lecture 29. Today we're going to be talking about a generally loaded transistor. This is good knowledge to know if you're interested in doing inspection analysis. But before starting, as usual, announcements. Homework number 9 is online. It's due this Friday. You will get another homework probably this Friday or sometime in the weekend, but it won't be due till 2 weeks after that, because the week coming up in 2 weeks from now is your midterm number 2. Okay, I guess before that we extended lab not 5. You know that's due next week, November 6th on Tuesday. But midterm 2 is coming up in less than 2 weeks now. It'll be Friday next week, November 9th at 5 p.m. in 277 Corey, just like last time. Okay, this time I'll try to see if the person who has the classroom afterwards is going to be there or not. But anyway, more information on this midterm this coming Friday, but just be warned, you have a midterm coming up 2 Fridays from now. Other than that, any logistics issues, that sort of thing? How's that lab coming along? Who's finished? They don't want to raise their hands because they don't want to identify themselves on who's finished or not. But I will say that part of what we haven't been doing for this lab so far is actually measuring the CMU and CPI capacitors. I mention that every now and then. But you actually can do that using the capacitance meter that's in the lab. Okay, so you probably want to do that. If you want to guarantee that the transistor you've got can make the spec, you probably want to do that. And it's also good for you to do. You can measure CMU as a function of the VBC voltage, VCB voltage, the reverse bias voltage across that capacitor. And then from there you can use the techniques I talked about in lecture to back calculate CPI. Right? That gives you a better idea of what those capacitors are. And if you're designing this lab, you know those are very important capacitors to make sure you make this lab. Okay, so you probably should make an attempt to measure those capacitors as part of this lab. We'll make you do it in the next lab, which is a multi-transistor lab. But right now, that'd be a smart thing to do, so you don't have to keep fishing for transistors that can make the grade. If the spec is that hard, which I'm not sure it really is. Okay? Any questions? Any other questions? I guess there were no questions. I just made a comment. Okay. All right. So let's talk about inspection analysis some more. I did it last time, but I didn't give you all the tools that you need to be able to do it in a general sense. And so that's what I want to do as part of today. And so before doing that, let's just understand why we want to do this. So first of all, we're going to have multiple transistor circuits. Second of all, this transistor circuit that we've been looking at for a while, we can change it into all sorts of different configurations by merely changing the capacitors that we have around the circuit here. And so, for example, if I did something like this, same real biasing circuit, you got the 2R1 and R2 there, you got RE there. I took away RC in this case, and now I'm taking my output here. I've got a bypass capacitor to my output, which has a load resistance. My input's still going into the base in this case, and if I do this, then I end up with the common collector amplifier. Okay, and the common collector amplifier is typically called an emitter follower for reasons that I will talk about in a second. But basically what it does is it just follows the input voltage. It's like your buffer op-amp circuit, except not using a whole op-amp, just using a single transistor with a bunch of resistors around it. Okay, we'll talk about this in a bit. But by just changing the capacitor locations, the bypass capacitor locations, I get a very different amplifier than what I had before. This time taking my output from the emitter instead of the collector. Question up there.
So on some of your circuits, we had our standard amplifier thing. You have the CE, so it'll be
in parallel with RE, yeah.
Be out. Right, sometimes it'll be parallel with RE, or it'll be serial with VO. What's the difference? Like, do you do one versus the other for specific situations?
Yes, you just want a different amplifier. So in this case, if I took CE, so CE is just the capacitor that's attached to the emitter. I'll always call that CE. The E means emitter there. And so if I took that CE down in parallel with RE, then the small signal circuit would ground the emitter. And that's what we've been doing. So in this case, now I'm taking that CE out here, and I'm taking a different output. Before, our output was at the collector. You can't see my, there it is. Before, my output was at the collector. Yeah, so now I'm taking it off the emitter, but I'm putting the CE there to make sure that that shorts it straight to the output there. Okay? So everyone see what all I'm doing is switching the positions of my CEs and CBs and CCs. Don't even have a CC in this case because I've actually grounded or brought my collector to the VCC, which is a small signal ground. Okay? And so, right, if I turn this, by shorting these capacitors, I get this circuit down here, which is a very different circuit we've been looking at because the output is at the emitter now. Okay, I can continue to do this with that same configuration, except now I'll put a CB straight to ground here. Instead of having that CB as before, which goes to our source, I'm sending that to ground. And I'm now going to put my source where the emitter is. So I got my source resistance, and I got CE shorting that to the emitter, which allows me to put my input at the emitter. And then I have a CC at the collector, which allows me to drive my load by the collector. Okay, so in this case, if I go ahead and I short out all of these capacitors, I get this circuit, which I've now drawn in a different fashion to emphasize the fact that my input is now going into my emitter, and my output I'm taking out of my collector. So this is a different kind of gain. And finally, I can look at another circuit here. Not finally, I have an infinite number of possibilities here, especially as I add more transistors to this. But in this circuit, I'm going to return my input signal to CB. I'm going to do pretty much what I did before with my common emitter amplifier, except now I'm going to let some of that emitter resistor stay. Divided my emitter resistor into an RE1 and an RE2. I have this CE shunting out or shorting out this RE2 when it goes into the small signal circuit, but I'll keep RE1 in this circuit. Okay, so you see this circuit now, when I go from the large signal circuit to the small signal circuit, this is what the small signal looks like, exactly the same as what we had before, except now I have a resistor between my emitter and my ground. Okay, and so when I look at all of these different circuits, I'm pretty much always going to want the same thing. I'm going to want to know what the gain is, from whatever the input node is to the output node. I'm going to want to know what the input resistance is. I'm going to want to know what the output resistance is. I'm also going to want to know the frequency response of these things. So it's pretty much a generic thing that I want for all of these different amplifiers here. And so the question then becomes, what is the gain from the emitter to the collector? Okay, well, the way to get that is to plug in the small signal circuit for the transistor and do that analysis. So plug in the hybrid pi model, I mean, for the transistor, and then do that analysis using your KCL, KVL techniques that you understand. Even this one right here, when I take a look at this common emitter amplifier with degeneration, okay, if I look at this problem, one way you could try to attack this is say, okay, I have a resistor R pi there. That's going to be in my hybrid pi model, right? So hopefully you can all visualize that. But when you try to determine this input resistance here, some people will try to take that input resistance and write out that that input resistance is equal to the R pi that I see there and this RE1, because that's what's going to ground. Okay, so some people will try to say that that's equal to R pi plus RE1. Okay, does it look like that's what it is? It does look like that's what it is, but that is wrong. That is not right. Okay, and so I'm going to even write there that it's not right. Put an X there and everything. Why am I putting so many things there? Because every time I teach a class like this, I see this. I see someone coming in saying the input resistance Ri looking into the base of this transistor is R pi plus RE1. Okay, that's absolutely wrong. I'm going to tell you why that's absolutely wrong very soon. But it has to do with the fact that the current going through RE1 is not the base current. It's a very different current there, and you have to take into account that whole thing. Okay, so how do I go about attacking these other amplifier configurations. Okay, well, you can't do it without first doing some work, but as soon as you do that work, stop doing that work. Okay, and that's where inspection analysis comes around. So to help me with my inspection analysis, I want to be able to look at any transistor configuration and just look at it by inspection. But before doing it, I have to do work. And so here's our work now. The work that I want to do is to take a look at what I'm calling a generally loaded transistor. All right, so what do I mean by a generally loaded transistor? So, of course, the main piece of this is my transistor, but if I'm going to generally load this, right, in the general sense, all of its terminals can be loaded by something. And so in this case, for this class, I'm going to load all these terminals with some kind of resistance. In general, it's really going to be some resistance, capacitance, inductance combination or so. But in this case, let me just say it's resistance here. So the base, I'm going to load with some resistance, RB. The collector, I will load with some resistance, RC. And notice that I'm grounding all of their terminals there. I'm sending all these resistors to ground, an RE here, because in the small signal sense, they're always going to go to ground, right? All of our independent sources in the small signal sense, the DC sources, will go to ground. Okay, and so this is typically what we're going to get. And so in this case, I can look at this transistor very generally. I can look at this as not common emitter or common collector or whatever I've been calling these things, but I can look at them as gain from one terminal to the next. Okay, so this is my base terminal, that's my collector terminal. So this gain that I get from here to here, that I'm going to call common emitter. I've been calling this common emitter or common emitter with degeneration gain, but let me just now call this base to collector gain. Okay? So that's what that would be there, in that direction there. At the same token, I have all my other gains too. I can go base to emitter gain. And finally, I can go emitter to collector gain. Okay? So I have three different gains in this single device. And all I have to think about is, what do I have? Where's my input? Where's my output? And that's it. Input determines, which direction this arrow goes there. So why am I not going collector to emitter gain? I can, but then I'd be operating that device in the reverse active region. And I already said you don't want to do that because the device stinks in that region. Okay? So that's why I'm considering only these three gains right here, because those are the three practical gains we'll use for a forward active device. Okay, now on top of this, remember in our inspection analysis technique, it's not just the gains we care about. We also have to care about the impedances. We calculate gain stage by stage in inspection analysis. But while we do that, we have to account for the impedance or the resistance loading our stage as we try to get from one stage to the next. So you'll notice that I also can define impedance here, and these are now generalized impedances because this is now getting the impedance looking into the base, but assuming loading of the collector by RC and loading of the emitter by RE. And that loading is going to change a lot of things. Okay, so we have to worry about that loading. This resistance, and this is my nomenclature here, I'm going to call R little b. Okay, so R little b, the little b means that it's that resistance looking into that base. The big B in this case corresponds to the resistance loading that base, or the resistance looking out of that base terminal. Okay? Everyone have that? Okay, and by the same token, I can define all these other resistors too. So this resistor here looking this way, I'm going to call R little c. And this resistance looking up this way, I'm going to call R little e. Okay? And so that's my nomenclature as I go through this. And so now what we're going to do is we're going to find each of these gains, and we're going to find each of these resistances one at a time by plugging in the hybrid pi or the T model. And we're going to have to go through the work of doing that. We're going to have to do KCL and KVL. But once we get that answer, we're never going to do this analysis again. We're going to remember that analysis. We're going to remember the solution to that analysis. And again, it really comes down to memorizing about 6 equations. And once you know all those equations, you're going to be able to look at a transistor and hopefully not have to plug in the hybrid pi. Just know what the impedances are looking into the different terminals. Know what the gain is going from one terminal to the next. Okay? It seems so simple, but believe it or not, there are people who never learn this. Okay? If you read Sedgwick and Smith, if you read Gray and Meyer, you will never learn this unless you do these problems enough times. Then you pick it up over time. Okay? I'm not going to allow you to pick it up immediately here because we're recognizing right now what's possible. All right? So let's go ahead and do this. So first, let's start by finding the terminal resistances. Okay, so this means that the resistance, let me just say this, in other words, the resistance says seen looking into each terminal of the transistor. Okay, so let's start with R little e. Okay, so R little e is this resistance seen looking up into the emitter of this transistor. Okay, this is a familiar problem. We already solved this problem. We solved this problem in associated with finding the driving point resistance of the capacitor CE that was in parallel with RE. Do you remember doing that? Some people are saying yes, they actually do remember that. But that's great if you do. If you don't, you're going to have to look back in your notes because I'm not going to spend the time to go back to my notes there. But I'm just going to say we've already derived this. And I'll specify where it was. So this was in association with finding the RES, which is the driving point resistance for my low frequency analysis using short circuit time constant analysis. So we did this last time, which I know was Friday. It was the very last lecture, but that was a long time ago. But look back and see what we did, because I'm just going to write that answer. This is the answer we got. RE is equal to R pi plus my RB resistor divided by beta plus 1. Okay? That's going to be something that you should think about. When you look up into the emitter of a transistor that's generally loaded, okay, with RC and RB, okay, what you should see is R pi plus RB divided by beta plus 1. Okay? Now, what's R pi over RB? Okay, so these things you should know. Sorry, what's R pi over beta plus 1? These things you should sort of have in your head. This is equal to 1 over GM. Okay? It's actually equal to alpha over GM, but to me alpha is 1. Okay? So this, I can also write this as 1 over GM over whatever that base resistance was divided by beta plus 1. So that's another way that I can write this exact same equation. If you're more comfortable with this, then use this. But in the end, what you're seeing is that when I look up into the emitter, I see 1 over GM, okay, which is something I also called RE. So I'm calling this all sorts of things, but before That's also RE, little re. Okay? I see 1 over GM plus whatever's on the base divided by beta plus 1. Beta plus 1 is what? About 100. Which means I'm taking whatever's on the source of this thing and I'm reducing it enormously. So looking up the emitter, what I see is a very small resistance. Okay? That's the takeaway here. Looking up the emitter, I see a small resistance. Because 1 over GM is pretty small. What's 1 over GM for 1 milliamps? Okay, these numbers you should have in your head. That will help you less. 25. All right, so 1 over GM is about 25. Whatever RB is divided by beta, what would be in your lab? That's like 830 divided by 100. It's like 8 ohms or so. So it's a very small resistance there. Okay, I should say that all of this we derived assuming that R naught is much larger than RC. Okay, so that's a qualification, and that would be the case for most of our circuits. For some circuits that you'll see in 140, this may not be the case. Okay, so I'm just warning you, if you have R naught, if RC is on the same size as R naught, then this equation changes by a little bit here. But that's the equation. We already derived that. I'm not going to derive it again. Just go back to your notes. Let's move on to get another one of these resistances. And so that resistance, I want to get looking into the base of this transistor. Let's get this resistance RB. Okay, so if I want that resistance RB, and now I am going to cheat because I need to do this several times, so some apologies, but here's what I'm going to do. I'm going to grab this, and I'm going to copy it, and I'm going to keep it copied for the rest of this lecture, because I'm going to be probably producing that again and again. Okay, something very wrong happened there. Let me try that again. There it is. All right, so I want this little RB, which means I have to do a small signal analysis, and I'm going to do that, at least at first, by using my hybrid pi model. And so anytime you encounter something you don't recognize, plug in the hybrid pi model. Don't be afraid to do it, okay, because you might need to do it. And I will tell you later on what you can recognize and what you can't recognize. But when I use the word recognize, it's a very important word, because that's what circuit analysis is. It's all about recognition. If you can recognize things that you've seen before, that's how you can dissect an enormous circuit into something much easier to deal with. Okay? All right, so here's that hybrid pi model. So again, I'm going into the base of this transistor, and this is my generally loaded transistor. Let me bring it up again. I'm going to the base of this thing. And so that means in order to find this resistance going in there, I need to put in a test voltage source, Vx, and measure the test current that it sources going into this whole thing. And so in this case, the difference between what I've done before and now is I actually now have an emitter resistor that I have to deal with here. Okay, I also have on the output a collector resistor that I might have to deal with, but I guess I'm not really going to deal with it because I'm going to go ahead and neglect R naught again in this. So R naught in this case I'm going to neglect because I'm going to assume that R naught is very large. Okay, and so that's going to make my analysis a lot easier here. And so let's go ahead and do this analysis. And so what I want to first do is do a KVL over this loop right here. At least this is one approach that I could take. So if I do that, I want to define this voltage here as VE across that. And so I can write immediately with that KVL that Vx, which is the test voltage that I'm applying, is going to be equal to VBE plus my VE. Okay, but I also know that I have Ix flowing through this, so I know that VBE, I could write an equation for it as Ix times R pi. And then I also know that Ix is flowing through Re, but so is GM times VBE. So if I want the voltage across Re, which is that VE, right, VE is going to be that Ix plus that GM times VBE, all of that times RE. But I also know that GM times VBE depends on this VBE, which I already know what that is right there as a function of IX. So I can now write this whole thing as IX times 1 plus GM times R pi, and that whole thing times RE. Okay? Then from this, I could take all of these together and write an equation now for my Vx by putting all that together. That's going to be Ix times R pi, which is my VBE, plus Ix times 1 plus quantity GM times R pi times that RE resistance. If I factor out the Ix, I'm going to get Ix times R pi plus this GM times R pi I can recognize as just beta. Make the beta a bit bigger. Right? That's just beta. So in the end, this is going to be R pi times beta plus 1 times that RE, right? Which means finally, I can say that RB, which is the resistance I was looking for, that's just going to be this Vx over Ix. That's going to be equal to R pi plus beta plus 1 times RB. RE, yeah. Is that what you're pointing at? Okay. So it's going to be R pi plus beta plus 1 times RB. But I also know that beta, right, I already used this as GM times R pi. Okay, and so I can write this, and that's also much greater than 1. So I can take this and write this equation also as R pi times 1 plus GM times RE. Okay, so there's several forms that I have here. You can memorize any form you want here. But the main takeaway from this is that when I look into the base of a transistor, I do see the R pi resistance, which hopefully you can recognize right away because that R pi is right there in the hybrid pi model. But I also see a much bigger resistor that comes from whatever's hanging off the emitter. That whatever's hanging off the emitter gets multiplied by beta plus 1. Beta is a large number, right? So this is going to be a big resistor. Okay? And what do we want for the input for a voltage amplifier? We want a big resistor. This is how you do it. Okay? You simply put a emitter resistance there, for bipolar at least, to push that resistance up. So that's good for a voltage-to-voltage amplifier. And for other types of amplifiers that we'll talk about as well. Okay? So that was my analysis there, but you know what? This was the analysis that I did sort of brute force. Kind of stupidly done. There's a better way to think about this thing. Okay, so let's think about this in a better sense. And I'm going to think about it in terms of not the hybrid pi model. Okay, so the best thing is to memorize this. But if you ever can't remember this thing, just think of what situation you're looking at. And in this case, do that without thinking about the hybrid pi model. So in this case, I'm not going to think about the hybrid pi model. I'm just going to recognize a couple things here. Okay, first thing I'm going to recognize is that I have an R pi right here. I guess in a sense that is thinking about the hybrid pi model a little bit. But you know, you just have that R pi right there between the base and the emitter. Okay? And so I'm going to do the same kind of thing again. Vx and Ix. Except now I'm going to be a little smart about this. Because I don't need the hybrid pi model for me to know that if I have a base current here, IB, which is going to be equal to Ix, and my collector current I can write as beta times IB. Right? You know that. And you know by KCL the current running through this RE is beta plus 1 times that IB. Okay? So in the end, if I look at this whole thing, I can already write that the total voltage drop across this, Vx, is going to be whatever that IB is times R pi, that's Ix times R pi, plus whatever this is, beta plus 1 times Ix times Re, and right away, I once again can get, with very little trouble, this equation, right? So this, basically what you understand is this term here comes about due to amplification of base currents. Okay? So this is what you got to understand here. If you forget these equations, you can always get them back by what I call following the currents. Okay? In all of these transistor problems, if you follow the currents, you can solve them very easily without having to write any hybrid pi models. Okay? And that's what I'm trying to get you to do. Okay? So we got this by following the currents. Okay, if you ever take 140 with me, we'll talk about following the currents all the time, in addition to this inspection analysis that I'm teaching you right now. By the way, how many people actually answered that 140 petition from this class? Do you know, I, for some reason, cannot see the petition when I go on Piazza 101. So can you give me a count of how many there were? Was it just 8? Yes. Oh, you're raising your hand to say you responded to the petition. Yes. Does anyone have a count? Can someone get on Piazza now and tell me what the count is at some point later on today? They're talking about it, but if the count is not high enough, they won't do it. Okay. Huh?
What should the count be? Like around 10?
Well, I've been saying 10, but really 15 or something. Maybe even 20 would be nice. But if there were... Yeah, that's why I'm saying 15. To hold the course, right, you want about 30 or something, right? So that's why I say 15 would probably be it, because we don't know about the rest of the people who might want to take it. But, you know, let me know what that count is, whoever's finding that right now, and be honest about it, because I'll find out what it is sooner or later some other way, okay? So let's do this one more time, folks. That's one way to think of this, and so what I'm showing now is that there's many different ways to get the answer. Okay, there's not just one way to get the answer, but I'm going to do it one more time. I'm going to do it a different way. And this time, I'm going to use the T model. So remember that T model?
You said 11 people.
11 people. Okay. That's not bad. That's over the 10 that I was saying before. But I would say that if you really want this to happen, you should get 4 more. Okay? Because I've been discussing it with the other IC faculty. And we're basically saying 15. Right? If there isn't 15, we're not going to do it. And so if you can get that 15, well, there's still discussions going on. That doesn't mean they're not going to do it, but there's still discussions going on there. But they're starting to think about solutions. So get those petitions in if you want this to happen. And no one lie about it, right? Because if there really is 11, then there really is 11. Right? Okay? Anyway, back to this. So remember this model right here. And so I call that the emitter. This is the T model. And so usually the T model looks something like this. And I would do the same thing with the T model. Right, I would put in a Vx right here. I would measure the Ix in order to get what I've been calling that IB. But I can also call this beta times IB as well right there. Okay, so if IB is equal to Ix, then that's beta times Ix. This current going through all this, I'm just saying the same thing, beta plus 1 times Ix. And now this allows me to write RB, which is equal to Vx over Ix, is just going to be equal to, well, let me do this a little more slowly for you. let me write out Vx, right? So Vx now is going to be equal to just the voltage across this RE, little RE, big RE resistance there. Okay, so that's just equal to the total current going through that, which by the time it hits the emitter is going to be beta plus 1 times Ix, and that's now times little RE plus big RE. Okay? And so that means I can rearrange this to say that RB is equal to Vx over Ix, which is just beta plus 1, times little RE plus big RE. Okay? So that's another form of this now. And remember, RE is equal to 1 over GM, so that's beta plus 1 times 1 over GM plus big RE here. And since beta over GM is R pi, I can also reduce this to what I already had before. Okay, hopefully you can see that. This is exactly the same thing as what I got on this side here. This form, R pi plus beta plus 1 times RE, if I take beta plus 1 times 1 over GM there. But this is just another form of this that you can remember if you prefer. So it's yet another form of the same thing. And so now I have derived this 3 different ways. You have no excuse for not knowing this equation in the end. You should be able to see it by following the currents or just memorize the thing. Okay? Is that a question?
Yeah.
Oh, okay.
Just for clarity, RE is just between the emitter and any bypass capacitor that could be there, right?
You mean little RE?
Big RE.
Big R, big E?
Big RE.
This one.
Yeah, capital R, capital E.
This is just whatever resistance is seen looking that way, out of the emitter.
Okay.
That's capital R, capital E. Yeah. You're saying now, there's no such thing as a small signal resistor. Yeah, this is whatever resistor. It could be small signal, it could be large signal. So in other words, if I put a transistor there, if I had this, which you will have every now and then, okay, then if I'm looking down this way, what do I see?
CRC, the next one.
Yeah, right, the big RC, but in the end that's little R naught for this, because that's going straight to ground. It won't be if I have an emitter resistor there. Okay? And so we're going to get very general after this. I'm showing these resistors, but those resistors could be small signal resistors from other transistors. Okay? All right. So I think we've done enough with little RB looking at. Now let's get, big R, little b, looking into the base. Let's now get big R, little c. And I'll do this. Okay, and so in this case, I need to include all of my resistors here. So I'm just going to say, note that RB can influence it. So we'll include it in our analysis. Okay? And so hopefully I still have my oh, crap. Why did it go on that side? Okay, so I'm making sure that I'm here. Oh, I see. Because that's the same circuit. So let me try that again. It's almost faster to just draw the thing again. All right. So there's my small signal circuit. And so now I want to make this very as general as the original circuit there. So I'm going to hang out an RB right here. So that's the resistance seen looking out of the base terminal. I'm going to have an RE right here. and I'm looking for my R little c, and so I'm going to put my test voltage right here and measure that test current. Okay, now I cannot ignore R naught because it's right there in my path, and I'm looking for that particular resistance. I'm looking for this resistance seen right here, of course. That's my RC. And so let's start doing the same kinds of analyses that we've been doing here. So let me call this a voltage V little e. And why don't I do the analysis on the next page? And so I could say that my total voltage Vx is going to be the total voltage drop across all of these things here. And so Vx, if I take a KVL pretty much around here, well, let me start it here just because I'm doing KVL there. If I do my KVL there, then I'm going to say that Vx is going to be equal to whatever voltage drop I have across R naught. So that'll be R naught times whatever current is flowing through it. And the current that flows through R naught is going to be Ix minus this current Gm times VBE from that current source there. And then I have to add to that my voltage VE. Okay? So I'll go on to this side now to continue that here. Okay. So usually for cases that matter, my RE is much less than RB plus R pi. So I'm going to go ahead and use a little bit of an approximation to make my analysis a bit easier. And write down what I just said. RE is much less than RB plus R pi. Okay, so then I can say, therefore, most of Ix flows through RE. Which means I can write that this VE voltage, that's about equal to Ix times RE. Okay? So I'll say this is not always the case. If I'm hanging this over another transistor, then this won't be the case, but there's going to be a very special case for that we'll have to derive for that as well. Okay? But this is happening mainly for the case where RE is much less than RB plus R pi. So I should say usually for us. For this class. Okay? And so if this is the case, then I can continue with my analysis, and I can now say that the current flowing through R pi, which I used to call Ix, but I'm going to call I pi now. So this current I pi is just going to be equal to the voltage across all of these things here, VE. This VE voltage is applied across RE, but it's also applied across R pi plus RB, right? So I can choose to say that this is going to be minus VE over R pi plus RB, okay, which I can now say, using this approximation up here, that VE is Ix times RE divided by R pi plus RB. Okay, therefore, I can write an expression now for my VBE, which is the voltage across that R pi. This should be the current going through that R pi. This is now going to be Ix times R pi times RE divided by R pi plus RB. Okay? And then from this, I could take all of the different things that I've written here, I guess including this one here. So let's take this and go here. So that's going to feed into this. This I pi will feed into this. And this VE will feed into that. So all of these then feed into an equation that I can write as Vx is going to be equal to Ix times 1 plus GM times R pi times RE divided by R pi plus RB. So you can see me using the VBE in there. That whole thing times R naught plus an IX times RE there. And so, therefore, rearranging this, I could say that RC is going to be VX over IX. So I'm going to pull out this R naught times this whole thing, 1 plus this GM times RE. But now I'm going to take that R pi and put it in the bottom of this. So I'll take this as 1 plus RB divided by R pi, the quantity RB divided by R pi. And that whole thing then plus RE. Of course, RE is a lot smaller than that R naught term there. So in the end, I can write that RC is about equal to R naught times 1 plus this GMRE over 1 plus this RB over R pi quantity, close. And then even this, if I have the case where R pi is much greater than RB. So if I have a small RB, which often is the case, this then comes down to R naught times 1 plus the quantity GM times RE. Okay, so this now becomes a couple forms for this resistance you're seeing looking down into the collector. Okay, and the main thing that you're finding here is that this is even bigger than R naught. Right, so this thing here that means it's very big. And sometimes you need that very big when you want to make a current source or an active load or something that we haven't talked about yet, but you want a very large resistance. This is one way to get an extremely large resistance. In a lot of our analyses, though, this very big is just going to be swamped out by something much smaller, which means like a little, like an RC resistance that we have looking into this thing. And so we're rarely going to use this. Okay, a lot of times you're going to be able to neglect this. And so what I mean is something like this. So if I have this situation, which you're going to see many times again, right, and I'm looking at what's that resistance? Call that R naught there. Well, that's going to be the parallel combination. Call that R big C and R little c. I guess I got to put the slash down the C to make sure you know it's a big C. Oh boy. I should do that in the original one too. Oh really?
Yeah.
Oh my God. Okay.
You hear the big bell outside?
There is no big bell.
It's a huge bell, just like right here.
The bell is probably dressed in black. Okay, I'm almost done, sorry. Okay, so I just put the line down that RC. But in this case, this R naught is just going to be equal to that RC in parallel with that R capital C. But of course, that R capital C is huge. So this whole thing just boils down to RC. So in this respect, you almost never have to deal with this, that R naught or the R naught times this 1 plus stuff there. Right? You're usually just going to say it's RC, except if I load this with a transistor. So if I did this, put a PMOS on top of this thing, now I have to worry about that resistance going up. Okay? All right, so with that, I guess we'll end the lecture, and I'll see you next time. We'll continue with this next time.
Oh, this is where it is. Good.
Oh, is that yours?
Yep.
Excellent.